Okay, so I want to go over another superposition example. As I mentioned, something interesting is going to happen with this one when we short out one of the voltage sources. Let me go ahead and draw this schematic up. We're going to give ourselves a 12 volt source. And let's make that, 12 volts. We'll call this V1. We'll have an R1 that's equal to 12 ohms. An R2 that's equal to 24 ohms. An R3 that's equal to 8 ohms. And let's go ahead and put in one of these upside down voltage sources. And V2 is going to be equal to 8 volts. Okay, so from last time when we're applying superposition, well, first off, you couldn't solve this with just your basic rules right off the bat. We do need to apply superposition in this case because we have two voltage sources. And just to emphasize, we do have the polarity reversed on this V2 source, at least from what we're used to seeing. Now, as we know, we're going to have to solve this twice. And the first time we solve it, let's keep V1 and we'll short out V2. And then the second time that we solve this, we'll keep V2, but we will short out V1, effectively disabling V1. We'll come up with two solutions, and then we'll go ahead and take the algebraic sum of the currents, and we'll plug that back into our original circuit and see what happens. Okay. So let's go ahead, let's keep V1, let's short out V2. So I'm going to essentially imagine there is a wire from this side connected to this side. That'll effectively disable this source and just leave it with a wire in its place. So let's go ahead, let's do that. $12 volts. 12 ohms, 24 ohms, 8 ohms, and in place of V2 we have this short over here. Okay, now are we done? Can we just go ahead and solve this, or did the circuit fundamentally change somehow? Do we have something here? Check out this wire. When we shorted out V2, what did we just do? We put a 0 ohm wire in parallel with this 8 ohms. So what's going to happen to this 8 ohm resistance over here? Yeah, we're going to lose this 8 ohm resistor because it's in parallel with a short. And so all of the current, if you go ahead and look at what's going on here, the current would go through this 12 ohms, and then you would expect it to branch, but all of the current is actually going to go through this short here. So effectively, we've disabled the 8 ohms. And so in place of that 8 ohms, we just have a straight wire. This 8 ohm disappears. What about the 24 ohms over here? Don't we lose that as well? because this short is in parallel with not only the 8 ohms, but it's in parallel with the 24 ohms. So we're going to lose both of these. Okay, so let's go ahead, let's redraw this. And this short did not change this 12 ohms at all. We keep that because there was no short in parallel with the 12 ohms. It was only in parallel with the 8 ohm and the 24 ohms. So it was shorting around these two. So we lost both of these, and now the circuit effectively reduces to this, right? So this is a great type of exam question because notice very quickly the circuit reduces to a very easy problem. Right? So now we have 12 volts applied to 12 ohms. So do Ohm's law over there, and we get a current of 1 amp. And that is our first solution. Okay, so by disabling the 8-volt source, all we get is 1 amp running through R1 and 12 ohm, the R1 12 ohms, and 0 current going through these two. They effectively disappear here. Okay, so let's go ahead and let's disable V1 and solve this circuit again. Okay, so I'm going to redraw everything except we are going to have a short in place of V1. V2 is equal to 8 volts. We have an 8 ohm over here. We have a 24 ohm over here. And we have a 12 ohm over there. Okay, did anything here change as a result of us shorting out V1? No. This short is in series with the 12 ohms. That's not going to remove anything. This short is also not in parallel with anything else. It's not in parallel with the 24 or the 8 ohms. So we just have a circuit that we need to solve. So let's go ahead and let's solve that. To answer that question, yeah, all of the current goes around R2 and R3. R2 and R3 are effectively not doing anything in the circuit. So even if you constructed a circuit that contained R2 and R3, you would have no current actually going through those two. Everything would go through the short from the previous circuit. Okay, so let's go ahead, let's solve this. Positive on the bottom, minus on top. Okay, let's figure out an equivalent resistance for all of these. We have a 12 ohm in parallel with 24 in parallel with 8. So what I'm going to do is I'm going to put my 12 ohm in parallel with 24 ohms, and then I'll take the result of that and put it in parallel with 8 ohms. So I will pull up my calculator here. Let me first do the 12 and 24. So 12 times 24 divided by 12 plus 24. So divided by 36. And that gives us 8. And then now we have 8 ohms in parallel with this 8 ohms, right? So all I did was I merged these two. I got 8 ohms. Now I'm going to take that and merge that with the 8 ohms. Well, I have two 8 ohms in parallel. I'm going to get just half of one of those values. So I'm going to end up with 4 ohms at the end of the day. So this entire circuit reduces to 8 8 volts applied to 4 ohms. So the total current for this circuit equals 2 amps, right? Ohm's law, 8 volts divided by 4 ohms gives us 2 amps. Okay, so we know we have 2 amps in our original circuit going this way. Oh, great. What do we do now? Oh, we didn't even need to find the total current for this circuit because all of these are in parallel, right? 8 ohms is in parallel with 24 ohms is in parallel with 12 ohms, and we have 8 volts applied. So I have 8 volts across all of these. I should have started there. Okay, so if I wanted to know the current through each one of these, I could have just done, well, 8 ohms with 8 volts across it should give us 1 amp. 24 ohms with 8 volts across it. So that's just going to be 8 divided by 24 gives us 0.33333 repeating. Let me check out the questions. Can you repeat how you got RT again? Yeah, to get RT, all 3 of these were in parallel. So I did the parallel equation, 12 times 24 divided by 12 plus 24 resulted with 8 ohms. And then I had this combined resistance of 8 ohms in parallel with 8 ohms. 8 times 8 divided by 16 gives me 4. So that's how I got the total resistance. Okay, but as I showed, once we figured out this was 2 amps, that didn't help us further solve this problem. We needed to use something else, and that something else was, well, I just have 3 resistances in parallel with 8 volts applied. The 8 volts is in parallel with all of these. So I have 8 volts across each one of these, and then now I just apply Ohm's law. 8 volts divided by 8 ohms gives me 1 amp. 8 volts divided by 24 ohms gives us 0.33 repeating amps. And now I didn't need to solve this. I could just do 8 volts divided by 12 ohms. And we'll figure out what that is in a second. But notice here, I did calculate what the total current was. So the total current, Kirchhoff's current law should be applicable in this case. 2 amps going this way, 1 amp going this way. I should have 1 amp over here. The sum of all currents entering a node should equal the sum of all currents leaving that same node. 2 amps enter, 1 amp leaves. I must have 1 amp going this way. Well, same thing. KCL over here. 1 amp entering, 30.3333 repeating amps going up. I should get 0.6666 repeating amps going to the left. Now, hopefully, 8 volts divided by 12 ohms should give me 0.66 repeating amps if our whole system is consistent. So hopefully we get this. 8 divided by 12. Oh, thank God. Okay, good. So everything works. Okay, I'm just looking through some of the comments over here. I'm getting, how come when solving for this voltage source we have all 3 resistances, but when solving for the other voltage source we disabled R2? That's because we created a short over here, right? When we shorted out V2 to disable V2, part of the process of doing superposition, we had to disable this source, and that left us with a short in parallel with the 8 ohms and the 24 ohms. Short is in parallel, so that's why these two disappeared. But in this original problem, when we shorted out V1 it didn't remove any resistances because this short was not in parallel with any of these components. So that's the reason why the short disabled R2 and R3 the first time when we disabled the V2 source, but not when we disabled the V1 source. When we disabled the V1 source, it just left us with a short that was in series with the 12 ohm resistance here. So we didn't lose any of our resistances, okay? So hopefully are people less lost now? I see a comment that says, yeah, that lost me a bit. Does that answer your question? If you're lost, other people are lost. Let me put the two reductions right next to each other. Maybe. Okay, the top one was when we disabled the V1 source. The bottom one was when we disabled the V2 source. V2 left us with a short in parallel with 8 and 24, whereas when we disabled V1, it did not leave us with a short in parallel with anything. Yeah, cool. Okay, good. Okay, so we have our two solutions now. These are our two solutions, and we found that in our second solution we had 1 amp going to the right through our 12 ohm and this 24 and 8 ohms because they had no impact on the circuit. They had no impact on the circuit at all. We only got current going through this short with a value of 1 amp. So to be very explicit here, I had 0 amps here, 0 amps here, but I did have 1 amp going through the short, right? So now we can go ahead and apply superposition. We have our two solutions here. But notice these two had 0 amps going through it, and direction doesn't matter. Over here we had 1 amp going to the right and we had 0.6 amps going to the right. So let's go ahead and go back to our original circuit and let's take care of this 12 ohm resistance. Since we have 0.66 going to the right and 1 amp going to the right, we should have a algebraic sum. They're both going in the same direction. 1.66 amps. Okay, so where is my original circuit? Oh, here we are. 1.66 amps. Okay, that's what we should get for R1. Now, R2, what's the story behind R2? Well, with R2, again, if we look at it, 0 amps going through it in one solution, 0.33 amps going up in our first solution. So add these two together. We should have 0.33 repeating amps going up. So that takes care of R2. Let's go ahead and look at R3. In R3, we had 1 amp going up and 0 amps in our other solution. So we should just get 1 amp going up. Okay, so now this is what I should have according to superposition. Does this make sense? And we can actually use a couple of our rules to validate that this indeed was the correct approach to solving this. If I notice I have 8 ohms and I have 8 volts applied to it, right? So KVL is always going to be true for any circuit. Kirchhoff's voltage law never ceases to be applicable. And is there a closed loop here? Absolutely. Well, look at what's happening. I have 8 volts applied to an 8 ohm resistance. So I should have 8 volts across my R3. These two are in parallel, and 8 volts divided by 8 ohms gives us 1 amp. So yes, our superposition solution gave us the correct answer, and we've confirmed that with Kirchhoff's voltage law over here. The same thing can be done for this loop over here. Any closed loop, the sum of all voltage drops in any closed loop should equal 0. So over here, if I have 8 volts in parallel with my R2, I should have 8 volts across there. So 8 volts divided by 24 ohms should give us 0.33 repeating. Is that true? Well, let's do 8 divided by 24. Yeah, absolutely. 0.33. Okay, so with KVL, I've confirmed that my superposition solution is indeed correct. And that's kind of one of the nice things. You can check as you go using all of your rules, and it gives you a ton of practice. And it's one big complete system of rules that works. So this is the end result. If you wanted to further solve this, obviously this is going to have 8 volts across it. This is going to have 8 volts across it. And over here, if I look at KVL, I should get 12 volts minus 8 volts across the 12 ohms. Actually, no, wait, is the polarity... I should actually look at this, because it goes from a higher voltage to a lower voltage, goes from a higher voltage to a lower voltage. So if you do the KCL loop over here, I get 12 volts plus, let me do it in blue. Actually, I'll just start here and let's write plus VR1, keep going, minus 8 volts, keep going, minus 12 volts. I'm back at where I started, set it all equal to 0 volts. So I actually have 20 volts across my R1. And if I do 20 volts divided by 12, I get 1.66 repeating amps, exactly what we said. Okay, so little roundabout application of Kirchhoff's voltage law there, but just to confirm the current through R1 as well, very similar to how we applied KVL in the other two cases. I just had to explicitly write it to make sure that I got my polarities of my voltage drops correct. It wasn't as straightforward to see as, say, this 8 ohms, where I only have one voltage and one resistor in this loop. In this case, I had a few different things going on. So that's one of those cases where I'll write it out to make sure that I don't screw up Kirchhoff's voltage law with its application. But it confirmed exactly what we got. So now at this point, you have your voltage drops across everything. You have your currents through everything. You can figure out the power dissipated for R1, R2, R3. So this is one of those problems that can actually be solved pretty quickly. And that's why I've given this in the past as an exam question. Hint, hint. Okay? So I know we're getting close to our exam. Are we in week 5 right now? Are we in week 5? Yeah, next week is week 6, right? So I think we're going to be having an exam. I do want to cover Thevenin and Norton circuits before we get to the first exam. I think we will do Thevenin and Norton circuits after the exam. Let's go ahead and let's do the first exam on Thursday. Next Thursday. What day is it today? Today's Tuesday. So actually we will be able to have a Thevenin, because we're going to cover Thevenin equivalent circuits on Thursday. This Thursday. So let's go ahead and let's establish midterm 1 is going to be next Thursday. The first. Okay, so 10-1 is going to be midterm exam. Okay, so we'll go ahead and have that on the 1st. Okay, and so this coming Thursday, let's see, that would be the 24th. We'll cover Thevenin, and then I think the following Tuesday we'll cover Norton, but I will have at least one simple Thevenin equivalent circuit on the first exam. So that'll give us the weekend and Tuesday to answer any questions about that, and then our exam will be everything that we've had up till now. Okay, there is some prep material on the website. I hope, I don't put the website material up there just for me. So hopefully you've checked it out, how to look at it. Let's take a look at 211. There is some homework, some midterm 1 prep material, and I even have a midterm 1 sample with a solution on there. So this is an exam I've given in the past. It's been up there since the beginning of class, so hopefully you've taken a look at this. And all of my solutions I've given for this particular exam. Okay, as well as homework and some questions, all the topics that I would ask for. The only thing is, we should also add Thevenin to this, but we're going to cover that on Thursday. So I'll go ahead and talk more about Thevenin on Thursday. Okay, do I have any questions thus far? Any questions? How will the exam be given? Oh yeah, that's a good question. Online, on Beachboard. So it will be a quiz on Beachboard, and the exam, yeah, will be in that quiz format. You can use, it's all open notes. I mean, we're at home in front of our computers. The last thing that I'm gonna say is, oh, you can't have any books or notes. No, it's open book, it's open notes. The only thing it isn't is open Discord. No open Discord. And so the way, let's see, what I want to say as far as the format of the exam. So the format of the exam would be, you know, these types of questions would be here. I throw in a few conceptual questions in the beginning, some stuff on, you know, basic atomic theory, conventional flow, electron flow. And so each question would be usually containing an image like this, or an image of a circuit, and then would ask you for the values that I'm interested in finding. Okay, so they would be one line entered in answers. Make sure to put units, right? If the question is asking for IR1, make sure you put in the milliamps. Make sure you have amps. Make sure you know, whatever unit is appropriate for that solution, go ahead and write out the units. If you just list 20, I'll be deducting for that, because I don't know if that's 20 amps. I don't know if that's 20 microamps or 20 milliamps. So make sure the units are specified. And so it would just be text answers, right? So just a line for each quantity that I'm interested in asking about. And so I think a good question is, knowing that the exam would look like that as a Beachboard quiz, what should you have on your desk? So when you go ahead to take this exam, and you're gonna want to have some paper readily available. Absolutely. You're gonna want to have blank paper. You're gonna want to have your pens, pencils, whatever it is that you use, and your calculator. And you want to be able to do these as quickly as possible, get those answers in, and then move on to the next one. So a word of caution. No, there's no multimeter on the, no multimeter that you would need for the exam. But what I would have on the exam is maybe a question about breadboarding, or a question about taking a measurement from a breadboard. Those types of lab soft skills I can definitely ask about. I can ask questions about the electroscope that we did that first day during lab. So things that pop up in lab are definitely free game on the exam. So have paper ready to go. I will be requiring the use of Lockdown browser that's built into Beachboard. So I'll be setting up a test quiz beforehand. This is not a quiz that's actually being graded. It's just simply so you can try out Lockdown browser and make sure that it downloads and works for you. Is that the Discord channel for the exam, or is that a Discord channel for preparing for the exam? There's a big difference there. So let's see. I'm trying to think of what else. What else? Oh, I should caution, the exam is definitely a little bit of a time crunch. So there's going to be probably more questions on this exam than you can enter in the amount of time that you have for the exam. Okay, the exam is going to be exactly 60 minutes long. And so if you don't finish the exam, that's fine. I'm not expecting everyone to complete the exam within the 60-minute period. Okay. That's a good question, Calvin. I'm not sure, but I think so. So because I'm putting up that test quiz that has lockdown browser, and let me make a note to set that up. And then you can test that out. But my guess is 99%. Yeah, probably it should work, because that is implemented by the school for lockdown browser. That's built into Beachboard. So, but I'll definitely give the chance to test that out and make sure that it works for everyone. I don't want any surprises on the day of the exam. Okay. So I'll send out an email once I put up that test quiz. So the only thing for midterm 1 topics, add Thevenin, which I will be teaching on Thursday. Okay. Oh, grading out of all questions. Some people may finish the entire exam. No, so the way I do grades is I grade the exam as a straight as a pure point value, and I enter that into Beachboard as is. Any curving that occurs happens at the end of the semester, once all grades are in. Any other questions? As far as the format or kind of what to expect for the exam next Thursday? Yeah, so in the grand scheme of things, it doesn't matter about grading the exam because it's compared to everyone else in class. So if everyone in class, if the best exam that gets turned in is 90% complete, then at the end of the semester, when I go ahead and curve all grades, everything balances out anyways. Of course.
So, hypothetically, if we all got a 0 on the exam, what would happen then?
Oh, what happens if everyone gets a 0? Well, let me put it this way. So if everyone agrees with each other to get a 0 on the exam, then as far as the exam is concerned, if at the end of the semester everyone has a 0 for the exam, then the exam doesn't matter. But that being said, if just one person enters in one correct value, all of a sudden that person got 100 on that exam and everyone else, right? I've thought about this system.
It makes it hard for us to unionize.
Yeah, exactly. Yeah, you could try. Also, if you plan to be on Discord and try to, so let me go ahead and get this out of the way. Look, if you're going to get together with a group of people and try to, let's just say, gain an advantage. So first off, there's other people in the class that may be more shy and may not have the social group to do that, right? So first off, cheating's really going to hurt them. And second off, if you know the answers, you're not going to lose precious time on the exam by trying to help other people, right? So it's in everyone's interest to work on their own and try to get the best score as possible, given that more than likely the exam's going to be longer and more than likely no one's going to finish it, right? Okay, so if there's no more questions, study the textbook and the sample exams. Don't sell yourself short on all of the practice that I have made available. There's also practice problems that are not listed on the website that may help. So no, you're going to have to practice from everywhere. It's just looking at the sample exam is not going to be good enough. And also keep in mind, I'm randomizing the exam. So each question gets pulled from a pool of questions. So there's like 4 different versions for each question that would be on the exam. And so when Beachboard generates the exam for each person, it's going to pull 1 of 4 or 1 of 6 from a question pool. And then so it'll pull that for each category that I'm interested on giving the exam about. And then it's going to randomize those on your page. So everyone will essentially have a different exam. So trying to cross-reference your exam with somebody else's exam is going to be a big waste of time that's going to end up resulting with a poor grade on the exam. So this is the only way that I've thought of to make this as fair as possible. My concern is making sure that someone that is shy in class or doesn't have, as many friends as somebody else that's popular doesn't get hurt as far as their grade. That's my biggest concern. So the exam is purposefully a little more questions than usual. It's randomized. There's a fixed time constraint on it. And that's as much that I can do to try and present as fair of an exam as possible. But I'm telling you this as warning so that when you see the exam, you just don't get shocked and go, man, that Eric, he's the worst person in the world. That's not the reason. I'm not trying to just give a hard exam. I'm trying to make sure that everyone has the fair and same opportunity to get as high of a grade as possible. That's what I'm ultimately interested in. And then given the randomization of the test and randomly pulling question pools, will make it, almost impossible to look at somebody else's in an online exam because you can't go number 3 or number 4. There are no numbers. It's just a question, right? And it may look similar to another question that somebody else has. And definitely don't want to put the correct answer for somebody else's different problem on yours because you think it's the same problem. It might actually be, one small value difference makes a huge difference in these problems. Okay, so another reason I want everyone to learn in this class. So if I tell you this information about the exam now, then hopefully that pushes more people to prepare more for the exam and ultimately get more out of the class. Okay? Okay, so with that being said, I'm going to go ahead and stop the recording now, and let's take a let's return at 10:30. We still have to take the measurements from the breadboarding and prototyping lab. So that's what I'm going to be doing during lab today. We're going to cover multimeter use and probing our breadboards. And so I'll be back at 10:30. All right. Take care, everyone. Yes. Okay, so to continue where we left off last time, we were breadboarding this circuit over here. Let me go ahead and just bring that up for a second. And from the lab document, let me pull up the lab document as well. Okay, so this was the circuit that we were prototyping. We had this 1K up here, 1K in the bottom. These were in series, and then we had these three resistances, the 4.7K and two 2.2Ks in parallel. And so if I pull up my... and also let's take a look at this 9-volt voltage source that we need to apply to this circuit. Okay, so if I pull up... here, we can see the breadboarded version of this circuit. Okay, so I have those two 1Ks, the 4.7Ks, and then the 2.2Ks over here. All three of these are in parallel, and then my voltage applied is going to come in from these two wires, my red for the positive and my minus side of my 9-volt source coming from the black wire. Okay, so we need to get 9 volts applied to this circuit. Okay, and so let me go ahead and kind of give a tour of my setup. Oh, and I'm gonna need a little better lighting. Let me go ahead and turn on my extra light. Okay, that should look probably a little better. Okay, so on my bench, I do have a few pieces of test gear, and I'm covering a lot of this stuff during those external sessions that I'm doing for my super cheap, affordable electronics workbench. So last session that I had, I did cover function generator, oscilloscope. Those are things we haven't used in class yet. Eventually, I will be showing them for the case of some examples. But what I want to bring you to is these two devices over here. Both of these are my benchtop power supplies. And so what does the benchtop power supply give us? So the benchtop power supply either benchtop PSU, which PSU stands for power supply unit. People will call it just benchtop power supply. They may or may not specify the unit part, or they'll just call it a PSU. All of these are essentially the same thing. And it plugs into our outlet. Our outlets in the US are 120 volts at 60 hertz. But that is AC. The whole point of the benchtop power supply is to give us our constant voltage source. So in our lab, we want a 9-volt constant voltage source. And so there's a few features that you're going to see in most benchtop power supplies. First off, they're going to give you a plus and a minus. And usually they give you something like a banana plug. Let me go ahead and show you what a banana plug looks like. So over here, and sorry, my voice is going to trail off because I can't stick the microphone on me. So here's a good example of, on our power supply, we have these banana plugs. So usually, if you had proper test leads, you would use something like this, and it plugs right in. And notice we have a plus and a minus on this power supply. I also have a second power supply above this with a few different features on this one, but it has the same thing. A black one for our negative terminal, and then for our positive voltage, we have this red one over here. That's generally the convention that we use, is black for negative, red for positive. And if you don't have banana plugs, because they do cost a little extra money, then what you can always do is, if you unscrew these, you can stick a wire in there. So I can always take a wire over here, put it into the back, and then you screw and tighten this down, and now you have a connection to just a bare wire. So you don't have to use the banana jack. You can just go in with a wire in the back, but it gives you some options at least. One of the nice things about these banana jacks, they do have another socket on the back, so you can keep on plugging these things into each other if you needed to for whatever reason. It does come in handy. But I'm just going to focus on the real simple, just going in and tighten a wire there. because that's more in line with what you guys would have available to you if you were in the CCS lab that we have there. Okay, now let me go back to our little diagram over here. So we know where we're going to get the positive and the minus. They're going to come from these two banana plugs or the screw connector. Now, I'm going to use a red wire for plus, and I'm going to use a black wire for minus. And I'm going to bring these out to my circuit. In fact, I have these little connectors that'll grab onto the wires on our breadboard. So I'll use those little grabbers or alligator clips in order to attach to these wires right here. So I would take the red and attach it there, and I would take the black and attach it down there in order to apply power to my circuit. So this benchtop power supply is going to be behaving like our 9-volt constant voltage source. Now there's another few features that a benchtop power supply actually provide. Now, first off, we need a way to change the voltage. So they usually have some type of a adjustment knob. So you can take that voltage knob and you can turn it to whatever voltage you want to provide. And different power supplies have different ranges of voltage. 9 volts is pretty straightforward, and so almost every power supply I've ever seen is capable of producing 9 volts. So we won't have any trouble providing 9 volts to our circuit. There's also another knob that says current, and I think this is a giant source of confusion. Okay, they put this knob over here on current. And now the question is, if I hook this up to a resistor, is it not the resistance that determines the current that is flowing through this circuit? Yes. So why on earth do they have this other knob on my benchtop power supply that says current? It's because they left out a really important word. Current limit. And almost every single power supply I've ever seen puts the word current and they don't write limit next to it. Okay, this is actually a little setting in order to determine what the max safe current is that this power supply will go ahead and put out. It's a safety feature. So we're not going to worry about this. Whenever you're using a power supply in the lab, just take this and turn it all the way to the right. Just allow the power supply to do max current. That way you don't accidentally run into a trouble where where the supply is limiting your current and you run into problems. So I would say, don't worry about this. Always just turn it max to the right and then don't think about it anymore. Okay? All we care about is providing a constant voltage. Now, the other thing that a benchtop power supply will give you is usually they'll give you some type of LCD that displays the volts over there. So as you go ahead and turn this knob, you're going to get different voltages on the output because this is an adjustable benchtop power supply. We have the flexibility to change what the voltage is out. And that's really all we need to know about a benchtop power supply. Now, as far as making your own or having your own benchtop power supply, they're incredibly valuable. Almost every single group in 490 A and B will end up having, by the time they're a senior, will have some type of adjustable power supply that they will use for their own projects. So this is where I'll point you to my next kind of fundamentals electronics workbench session that I'm doing in 2 weeks. If I switch back over to my browser, and I go to the website, my website, and go over to the Electronics Workbench Challenge page, you'll see that I already scheduled the benchtop power supply and multimeters test. This is probably a really good session for 211. We're going to be going over those multimeters. We're going to be comparing them to each other. We're going to see if that $20 multimeter is a good bargain. I don't have an answer yet for it. I have to test it, and I'll be testing them live. But we'll also be making a benchtop power supply in that session. Okay, we're going to construct it from a power supply unit for a desktop PC. You can go out, you probably have some old computers that are retired, probably throwing them out, or they're in the garage, or they're in a friend's garage, or you can go to your local dumpster and find one. Grab the power supply unit out of there. That's a very good high quality power supply that has many different voltages, and I'm going to be using that as my basis. So you can go ahead and read about what I'm going to be doing during this session, but just know that you can construct a very good benchtop power supply for under $10 easily. So I will leave that at that. You can check that out on your own. Hopefully you'll join me in the next session, not this Friday, but the following Friday. And let's go back to looking at our actual benchtop power supply. Okay, so this is the one I'm going to do that I'm going to use for this lab. And I'm going to go ahead, turn it on, and you'll see it gives me an LCD with the voltage. This one's a little more of a fancier benchtop power supply. This one's a little more basic. But it gives me a voltage readout. In fact, I'm already on 9 volts. And it also gives me the current that is coming out of the power supply. That's a nice feature. And in fact, for $15 more, for your homemade benchtop power supply, you can actually add all of this, the LCD and the current coming out of it. And it's actually, you know, that ends up turning into a $20 benchtop power supply, but it will be superior to the $50 ones that you can buy on Amazon. The Amazon sells like $50, $70 benchtop power supplies. I have people ask me about them all the time. The problem is they're kind of limited on what they can do. They only provide 1 voltage. We can actually get many different voltages and adjustability and a bunch of extra nice features out of a modified computer power supply for much less. You can have a nice full-blown do everything benchtop power supply for a long time for like $15 to $20. Okay, so we're going to go ahead and leave this on 9 volts. I have a black connection over here for my minus side. I have a red one over here for my positive side. So this comes out to these 2 cables, which, as I mentioned, have these little grabby things that I'm going to use to connect to my breadboard circuit. So let's go ahead and let's apply the voltage to our circuit before we start taking some measurements. I'm going to steal this black wire back from this top power supply. And let's go ahead and put it into our breadboard. Okay, so now I have 2 wires. red for my positive 9 volts and the black for the minus side of the 9 volts. I'm going to take, well, actually, let me clean up my paper over here so we don't have a bunch of clutter in the way. Let's take our breadboard. I'm going to put this off on the side just a little bit. In fact, let's do this. Perfect. I'm going to put this at the top because we're going to be probing it with our multimeter. Now I'm going to go ahead and take the positive from my benchtop power supply, connect it to the positive of my circuit, and that is good enough for the connection. Next up, I'm going to take the black side from my prototype, from my breadboard, and I will connect that to the black one. And now I have power connected. I'm going to put these off of the screen over here. Okay, so now I should have power going to my board. Time for a smoke test. Okay, let's switch back and take a look at what our benchtop power supply says. Okay, looks like I'm at 9.01 volts. I would say that's fine. That's 9 volts. I know it's 9.01 volts and not 9.00 volts, but that's completely acceptable. If I really wanted to, there, I can change it so it's exactly precisely 9 volts. One thing you're going to find is power is not, generally speaking, not that precise. 9.0 versus 9.1 is not that big of a deal. I would call them all 9 volts in that case. Okay, now we can notice we are actually drawing some current, and I'm not sure the precision of this current measurement over here, but it looks like we are drawing about 10 milliamps from the power supply, and that we have about 90 milliwatts of power being dissipated by our circuit. Okay, now again, these LCD displays on your benchtop power supplies are really not as accurate as your multimeter. Your multimeter always does a more accurate job of measuring voltage. So let's go ahead and let's take some voltage measurements from our circuit. See if I can fit all of this on here. Okay, now as far as using the multimeter, I want to take some voltage measurements right now. So we're going to have to set up a few things on our multimeter. First off, let's make sure our probes are connected to the right terminals. Black always goes to common. The red probe, if we're measuring voltage, over on this connection, it says V above it. So if we're going to measure ohms, if we're going to measure voltage, if we're going to measure capacitors and other fun stuff, then we use this connection. So just make sure your probes are connected to the right point. Black on common, red on V. Now let's make sure that we set this to V for voltage. Notice we have milliamps, microamps, actually this is degrees Celsius. This multimeter also has a temperature probe. Okay, so right now we're measuring voltage between these two probes, and it looks like I got some noise coming over. That's fine. How much voltage do my fingers provide? About 0.1 volts, right? Okay, so let's go ahead. We have power applied to our board. Let's first take a voltage measurement of the power coming from the benchtop power supply. So I'm going to take my black probe and I'm going to go to this side of the resistor down here and the top side of the resistor over here, and that should give me a measurement of these two wires. Now, here's my advice. When you're probing a breadboard, use the point where the component plugs into the board. Where that plugs in, if I take my probe and I gently press down, I'm going to make a good solid connection with that conductor right there. Okay, so that's how I take a good precise measurement from my breadboard. I'm going to do the same thing for down here, but I'm going to reposition this wire so that you can see where I insert down here. And it looks like 8.97 volts. Okay, I can do a little bit of tweaking in order to get that exactly 9. I can change things on my benchtop power supply. So you can watch my multimeter as I slightly increase the voltage to make it exactly 9. Okay, that's a solid 9 volts. And so before I do anything with my benchtop power supply, generally speaking, I want to measure that supply, make sure it's the correct voltage. As I said, the LCD on the front of most benchtop power supplies is not that accurate. Your multimeter is always more accurate. Okay, so now we have a perfect 9 volts feeding into our circuit. Okay, now we're going to go ahead and step through the voltages for each one of these. I need to pull up my lab document. Okay, so we are going to start with measuring R1. One of the nice things about setting up your breadboard such that it looks just like the circuit is it is going to make it so much easier to identify which component goes where. Okay, so this is R1 up here. I'm going to go ahead and measure the voltage of R1. So you're going to want to be recording these values. So I'm going to again insert my probe right where the lead goes into the breadboard, and I'm going to squish it down a little bit with the tip of my probe, and then we can read the voltage across it. It looks like 3.112 volts. Okay, 3.112 volts. That's R1. That's V sub R1. Okay, let's go ahead and do the next one, R2. R2 is going to be that 4.7K. I'm going to probe there and at the bottom. Again, I'm just going to go into the breadboard right where it makes contact. 2.789 volts is the voltage drop across your resistor for R2. Okay, let's go on to the next. Let's do the other one on the bottom. This is R5. R5 is that 1K resistor. Let's find out what the voltage is across those. Okay, looks like 3.1 volts. Okay, 3.102 volts. That's across R5, our 1K resistor. Now you might be asking, why is it negative? Well, look at my probes. My positive side is attached to the lower voltage side. Hello. Okay, so I have my red probe attached to the black side. This is the negative of the benchtop power supply. If I go ahead and reverse it, it'll say 3.106. Okay, so negative if I have my probes reversed from where the assumed higher voltage side is. Okay, so that takes care of the voltage drop across R5. Let's go look at the voltage drop across the 2.2K R3. 2.783. This is the voltage drop across the 2.2K resistor R3. 2.783. Or 8.2, whichever you want. I'm not that worried about 1 millivolt. Okay, let's go ahead. Let's check the voltage on the last one. This is R4. .789, 2.790. Okay, 2.79. If you look, this 2.2K is in parallel with this other 2.2K. I'm expecting them to be the same voltage, 2.79. Okay, 2.785. That's not much of a difference. These two have the same voltage drop across them, okay? Why is one slightly higher than the other one? Because we have these wires are not perfect. The breadboard is not perfect. We have little tiny voltage drops across these wires. So you're not going at, when you're using a breadboard, you're not going to get millivolt precision. And I'm not even sure how precise my multimeter is. This is my best multimeter. It should be pretty good, but we also have long wires. These long probe wires also have a little bit of resistance, okay? So these wires are not perfect. On the board, we treat wires as being perfect because it makes things much easier. But in truth, when you have long wires, they have a little bit of resistance. Okay, so you are going to be off a little bit on the millivolt scale. Okay, so someone has gone ahead and posted the voltages. Now what I want to do is someone else bring up their completed hand calculation and the simulation values. Does anybody have that document filled out that they are willing to share and do a screen share on it? If not, that's okay. Don't worry about screen share. Just tell me, are the voltages matching? What did you get for VR1 in the simulation? Okay, so in the simulation in LT Spice, you got 3.1, wow. You got 3.1127 on the simulation? That's because I have good equipment over here. Okay. That's because I have a decent quality multimeter, and I measured the voltage at this point, and I adjusted my benchtop power supply earlier. That's why these values are coming out so spot on. It's because I took the time to go ahead and probe over here and adjust my benchtop power supply. You don't need a precision benchtop power supply to do that. You just need one decent quality multimeter, okay? And you can also get good results from your own prototyping, okay? This is more about skill and knowledge than it is the quality of the equipment that you are using. Where I can't sacrifice on is a multimeter if I want to get reasonable values to be measured. Okay, so that's why I say don't go for your super cheap multimeter, but you can get a super cheap benchtop power supply, because at the end of the day, this is the value that I'm going to adjust it to. So one reasonable quality multimeter is all you need. And quite frankly, for all other test equipment, you can go super cheap on, and it's not going to make that big of a difference. Okay. So our voltages are good. We need to measure current. Okay. Now, this might be the most important part of this lab. I'm going to move my breadboard out of the way. And I am recording this, if anyone was wondering. Okay, I'm not going to get too much into the reason for why things will break if this is done incorrectly. But my point is, if we don't measure current correctly with our multimeter, we can damage, and they put a fuse in your multimeter for a reason. You'll blow the fuse. You'll blow the fuse, you'll damage the multimeter, you'll damage your circuit, you may damage other things like your power supply. Okay, so this is very important. When I'm measuring voltage, it's not that big of a deal. If I put these probes in the wrong place, it's not that big of a deal. But when I'm measuring current, I really need to take my time and make sure that I'm measuring it properly. It's not as easy to measure current as it is to measure voltage. And no matter how many times that I say this and I go over this, people are still going to do this incorrectly and damage their multimeter. And I'm not going to feel bad. Okay, if we take a circuit and let's just say we have something super easy here, 12 volts, 12 ohms. We should have 1 amp. Okay, to measure current with our multimeter, we need to cut/disconnect the circuit or the component and place our digital multimeter in series with where we want to measure the current. Let's go ahead and let's say I want to measure the current going through this wire. I need to physically disconnect the circuit, okay? I need to cut this wire. And now what I'm going to do is put my multimeter in series where I want to measure my current. Okay, you see what I did there? I put a disconnect. I cut my circuit. I opened it up and I finished closing my circuit again using my multimeter set to current. Okay? So we are completing the connection with our multimeter. Okay. If we don't do this, if we treat it like we're measuring voltage and I just set my multimeter to current and I put my probes across like this, I will break something. So make sure you actually disconnect the circuit and put your multimeter in series. Look at where the current is going now. I need the current to go into my multimeter and come back out. You can think of this as the multimeter is counting the electrons that it sees per second. Okay, I need the electrons to flow through my multimeter and then finish going through the rest of the circuit. Okay, I cannot just probe across a component and take a measurement that way. I will break stuff. Okay, don't do this. Your multimeter and your power supply will suffer and or break. Okay, so don't ever do this, please. Okay, if I want to measure the current going through this component, let's make it a more complicated circuit. Okay, if I want to measure the current going through here, I need to disconnect and then put my multimeter in series. Okay, so I just disconnected it. And then I put my multimeter in series. Okay, so don't ever measure with current across a component. Voltage is measured across. Okay, so let's go ahead and let's apply this to our circuit and let's get some values here. Okay, so to measure current, I have two different ranges. Actually, most multimeters have a milliamp range and an amp range. Now, the caveat is if I need to measure current greater than 500, right here, greater than 500, then I need to use the 10 amp range. It's a physically different connector. But if I'm going to measure within the milliamp range, then I want to use the milliamp range for a more precise measurement. Okay, so I'm moving my probe from the voltage setting to the milliamp range. Now, if I don't know what the current is, then I would start with 10 amps, make sure it's safe, and then move down to the milliamp range. But because I checked the voltages already, I'm confident that this is all safely within that 500 milliamp range. So I'm not at danger of blowing a fuse here, okay? Now make sure you also set the probe or set the multimeter over to the appropriate units for milliamp for measuring current, okay? And now let's say we want to measure the current going through R1. Okay, again, I am not going to do this. I need to physically disconnect and put my multimeter in series. To make this easier on myself, I'm just going to disconnect and I'm going to move it over to a different unused set of 5 connections on my breadboard. Okay, notice I just disconnected my circuit. I should have 0 amps flowing through my circuit at this point, right? Sure enough, I read 0 on my power supply. Okay, now let's go ahead and complete the circuit with my multimeter and see what the current is. So again, I'm going to use my technique of putting my probe into the breadboard where the conductor inserts into and wedge it in there so I make a good connection. And then I'm going to finish it on the other side. Okay, my measurement for the current going through R1 is 3.10 milliamps. Okay, someone tell me what they calculated or what they got from the simulation for the current going through R1. Awesome. Okay. So things that we have learned today. Turns out Eric is all right at measuring things. Okay, I'm going to reconnect R1. And now I want to measure the current through, what's this guy? R2. Again, just like I did in this image, I'm going to disconnect this resistor at some point. I can disconnect it down here. I can disconnect it up there. It doesn't matter. But either way, I need to disconnect it and then finish the circuit with my multimeter. Okay, to make it easy for myself, I'm just going to pull out the leg of my resistor and I'm going to put it into an unused group of 5. Okay, so I've disconnected the resistor from the circuit, and now I'm going to finish the circuit with my multimeter. So I'll probe from where I took the resistor out, and I'm going to probe where the resistor starts back up again. Looks like I'm getting 0.57 milliamps for R2. What did you guys simulate or calculate for the current going through R2? Spot on. I'll take it. 0.57. That's a very small amount of current. That's 570 microamps, right? You guys calculated 0.59. I got 0.57. Okay, my multimeter is a little less accurate in those smaller currents. But when I created this lab, I chose small currents so that everyone was safer with small currents, right? So 0.57 versus 0.59, I'll take that all day long. Okay, let's reconnect that one. Let's go ahead and let's look at R5. R5 is this bottom resistor. Okay, now the current going through R5 should be the same current going through R1, right? If you go ahead and look at our circuit, the current going through R1 is our total current. The current going back into our 9-volt source going through R5 is also the total current. This should be the same value as what we had up here. Let's go ahead and check that. I'm going to do the same thing. I'm going to disconnect. And I'll use a pair of tweezers so you can see it. Okay. So I moved it into an unused group of 5. Now I am going to complete the circuit with my multimeter. I got 3.10. That is the same that I got. Now notice it's minus. It's minus because I reversed my probes. Okay? Current has a direction, hence it has, well, the vector has direction, right? So positive or minus. If I switch my probe leads, I'll get a positive value. 3.10 milliamps. Cool. Now I'll reconnect that up. And now it didn't matter where I disconnected. I could have measured the current going through this resistor over here, or I could have measured it coming from over here. Again, I'll take my resistor and I'll move it to an unused group of 5. And I'll go ahead and take a measurement. Again, 3.10, right? Okay, current's the same at every point as far as when you're talking about things in series. Okay, so we got the current through these 3 components. Let's move on and measure the current going through R3. Again, I'm just going to take my resistor out. I'll move it over into an unused group of 5, and then I'll finish the connection. 1.24 milliamps. Okay, what did you guys calculate for the current going through R3? Okay, 1.24 versus 1.26. Awesome. We know that my multimeter isn't as accurate once you get into the tens of microamps. That's to be expected. Oh, I just lost my entire resistor. Okay, there it is. Let's go ahead. Let's disconnect the last resistor. Okay, so I left it connected in the same group of 5 down here, but I disconnected it here at the top. Let's go ahead and let's finish taking the measurement. Okay, we have 1.24 milliamps going through R4. What did you guys get? I assume you got 1.26 as well. 1.26 milliamps. Yep, cool. Okay, so that is voltage measuring, current measuring, and the usage for the benchtop power supply. Okay. Now, I'll also kind of say again, the session that I have in 2 weeks for the benchtop power supply is a really useful one. That's going to be multimeters and benchtop power supplies. That's exactly what we did here in lab today. If you want to have your own benchtop power supply, please come by. Read up on that webpage, and you can read about sources for getting a desktop ATX power supply from an old PC or from a friend's garage or from your local dumpster. Or if you really have to, you can, I guess, buy one off of Amazon. I think they're like $25 is the cheapest that I've ever seen. But at that point now you're spending more than you need to for a benchtop power supply. So I'm going to go ahead and finish today's session off with that. We have current for RT. Oh, do we use the DMM to calculate the total? Sure. Let's go ahead and measure the resistance for the whole circuit. I'm going to turn off my power supply. It is now off. I'm going to go back to my whiteboard. I'm going to disconnect the power leads from there. I'm going to set my multimeter to resistance. Make sure we have the probe in the correct hole over here. This is for measuring ohms. And now let's go ahead and take a measurement for the total resistance. I'm going to start from one side, and I'm going to go to the other side. 2.88K. Okay, 2.88K. That is the measured total resistance. Now, last class, we measured each one of these resistors with our multimeter. But keep in mind, if I measure this resistor while it's in the circuit, if I put one probe here and one probe over here, I'm going to measure all of the resistances in that circuit that are in parallel, okay? So you have to pull the resistor out of the breadboard and then take a measurement. This is supposed to be a 2.2K resistor, but I'm reading 0.89K. I'm reading 890 ohms. Okay, that's because I'm measuring not only the 2.2K resistor, but I'm also measuring this 2.2K in parallel, as well as the 4.7 in parallel. Okay. Let's see. For your hand calculation, what did you get? You got 2893. 2.88. I'll buy it. That sounds good enough to me. We're off by what, 10 ohms? Big deal. These resistors are each 1% tolerance. That means that your 100 ohm resistor can be 101 ohms or 99 ohms, plus minus 1%. So that's true for all of these. When you get into the higher values, that can make a large difference. $2,891. Yeah, that's fine. Okay, so I'm done with today's session. I will be, I gotta merge some of these videos together and then post them up. I think this is actually one of those good lab videos because it goes over together with the previous lab video, how to set up a benchtop power supply, how to take voltage measurements, current measurements, that whole issue with having to disconnect your circuit and put your multimeter in series. Guaranteed I will ask some questions about that on the exam. That one's super important because I don't want people blowing up their multimeters needlessly. Okay? So expect an exam question on measurement with your multimeter for voltage, current, and probably resistance. Okay, so I'm going to stop recording at that point, and I will see you guys later. I'll hang around to answer any questions here.